Collision detection. Collision detection, in general terms, is how we determine if two things, for whatever things we wanted them to be, are in some way, shape, or form intersecting. These are basic mathematical or geometric tests to see if something is inside of something else. In order to start talking about collision detection, we need to start talking about shapes. So when we're talking about 2D space, well, look, there's a whole shapes thing. We're talking about things like axis-aligned rectangles or circles. I want to make sure that's a circle, not a ellipse. You're also going to have things like edges and, of course, points, which I'm going to just make a tiny circle. Into the fill color too, also that. Cool. How these things will interact with each other will require some kind of mathematical test. So the first thing for collision detection to work, we need to have a test to see if shape A and shape B are in any way, shape, or form intersecting. So, and by the way, they're more than this. Like you can think of any kind of polygon as well would apply. So if we have triangles, there are triangle tests. In fact, all of 3D math is based on triangle for whatever shape the triangle happens to be. And we have even more complicated shapes. Although once we start talking about more complicated shapes, like a 12-sided polygon, or perhaps, let's do, here, a polyline. So arbitrary shape here. Oh, no, I should move that one later. Yeah, I don't want any intersections here. So any kind of polygon here. All of these are potential things, but once we have this complex things, honestly, anything beyond a rectangle or circle, we start dealing with just line intersections. So with the line intersection tests, once you have those working, we have all of the rest working. So these are all basically the same test. The reason I'm talking about things like axis-aligned bounding boxes or perfect circles is because optimization is going to be something that we're always considering. Now, I'm always saying to my students that programming is an act of discovery, which means don't worry about having it perfectly understood before you begin. That will come as you start learning more. So to start with, I would always say, just see what you can figure out on your own and then start looking at the algorithms. They'll make more sense. As soon as you start, if you start first from the algorithmic, the abstract, it's sometimes hard to make that connection. But once you've built and seen the need for something and understand the domain of what's going on with whatever problem it is you're trying to solve, then when you reach out to the algorithms, they'll make a lot more sense. Like, oh, okay, I see how this can solve my problem. If you're one of those people, who I am not one of, who can understand the abstract first and then immediately turn that into code and solving problems, wonderful. I don't need to talk to you about that. You've already figured that one out for yourself. For everyone else who has dealt with the complexities of algorithms and looks at it and goes, what? I find it much more useful to look at the real world tangible application first, and then we'll start talking about optimizations. But to make our lives simpler, it also is sometimes handy to look at something like an axis-aligned bounding box. So this is not rotated. This collision test versus that collision test are very, very different things. So for a lot of games, even modern 3D games, you will approximate your collision shape, even if it's in 3D space, a collision volume, in an axis line bounding box. But the reason why that's great is because we can treat each dimension individually. Let's take a look at what that would entail. So let's continue this. Only I want to talk about the bounding box. So we have two dimensions here. We have our x and our y. So I'm just going to keep this as a little reference up here, and this one as well. And let's label these. So we have our x-axis y-axis. And by the way, this is positive y, and this is positive x. When we're talking about 2D screen space, so the top of the screen, top left of the screen is always going to be 0, 0. The bottom right of the screen is always going to be the max width and max height of our screen space. When we're dealing with 3D math, usually things center around the origin, and so that the screen would be positive and negative, with 0, 0 being at the dead center. But for 2D space, the tradition is top left is 0, 0, and then it's positive y moving down. So that's the 0 y, and that's the positive y. We're not going into the negative space down here. It's different in other coordinate spaces. It can take some getting used to, especially if you start looking at some mathematical equations online. Generally speaking, the up is positive when we're talking about how most Cartesian grids are written out in mathematical world. But just the way that computer technology started indexing from the top left corner and then moving out from there, that's how we ended up with positive y down in computer screen space. And then, of course, once we move to 3D space, that also goes out the window. We go back to true math. All right, enough about that. So we have an axis-aligned bounding box, which means, in this case, my bounding box is completely contained within the negative x and positive y coordinate, or negative negative, or positive positive, wherever it's going to be. Just keep that in mind as we're referencing things. If I want to determine if, let me grab my point over here. If I have some arbitrary point, and I want to determine if it's inside the bounding box, let's talk about how we can determine that test. So if, again, I have a bounding box, and this corner is going to be my xy position in 3D space, or 2D space in this example. So that's my xy, and then this is my width, and this is my height. So my bottom coordinate would be specified by x plus width, y plus height. There are other ways you can handle it. You can keep this coordinate and that coordinate. There are ways of handling a center point and then two offsets. I find this is a good way of keeping track of things without having to keep multiple numbers in sequence together. What that means is if I were to keep the top left and bottom right corners in memory, so I have an x1 and y1 and an x2 and a y2, anytime I move the rectangle, I would have to update two sets of coordinates. By just keeping it x, y with height, I only have to worry about the x and y changing. All right, so let's talk about the test that we're going to have. Now, if I have just a point, a reference point, we're only going to have an x and y. Collision detection is one of the times, and there will be many in your programming careers, where sometimes you want to test for the positive case, sometimes you want to test for the negative case. What I mean by that is sometimes you can reject something, and that is the easier way, the less math to do. So, for instance, I can check to make sure that my x coordinate is greater. So let me even label this even further. I'll call this P. Oh no, I'm looking at this, it's starting to look like math. And we're going to call this R as my rectangle. All right, so I can check, once again, some more math here. Positive test would be if, stop capitalizing, P dot x is greater than R dot x, and P dot x, and this is just looking at one dimension now, is less than or equal to R dot x plus R dot w. So this would test to make sure that this point is within this. And then we want to check, let's add another layer here, and we want to check to see if the y's are also same. So over here we're checking height, and y, and y, and y, and y. I wanted two of those ampersands, thank you. So this would be a positive test. So if the x is greater than, or even you can make it inclusive. We can make it inclusive of the edge. So as long as our x is touching our rectangle's left side and within our right side, and then we're greater than or equal to our top and less than or equal to our bottom. So remember, because positive goes down, the less number is the top and the greater number is the bottom. If we were working in another coordinate system, that'd be basically the same question anyway. All right, so let me now write this as the negative. So now I can do if x, so this would be this would be then collide. Let's write this instead as a less than, and that's now an or, and this is a greater than. And then this also becomes an or. And so now the question becomes, if my x position is less than my left side, reject. Or if my position is greater than my right side, reject. Or, and this is also an or, my position is less than my top or greater than my bottom. And then what we do is then reject. Now, mathematically, these things look the same. But when you're programming, we have the ability to short circuit our if statements. So as soon as we can evaluate the entire statement as true or false, we don't have to evaluate the rest of the equation. So what this ends up becoming is, if my position happens to be over here, then I only have one check. As soon as I can reject, then we can have else collide. Here, I have to check to make sure all of these things are true before I can evaluate that the whole thing is true. Here, as soon as I can determine that one thing is not true, I can reject the whole thing, and I only have to test on the use case when it is true. So the only time I'll check all four is when we actually have a position inside our collision. Otherwise, and let's think about like the world of collisions with points inside rectangles, the vast majority of cases, it's probably going to be outside the rectangle, especially if we're doing some kind of like bullet hell where each individual thing is doing these tests. So most of them are going to reject, and then only the one thing is going to collide. So we want to reduce the amount of work we're doing. So this could, on the average case, is probably going to be one check or maybe two checks, and then we're done. Theory, if it's over here, I guess we have to still check all of it. But you get my point. The most use cases are going to be, we don't even have to evaluate the entire equation there. So start thinking about, maybe sometimes you want to reject rather than accept with your, what direction do you want to ask the question in. If we're doing something in loop, as soon as we can reject something, we don't have to go through the loop anymore, we can optimize our code by not doing any additional work. So that's how we would do a test for, a little note here, this is point in rectangle test. All right, that's one of them. Let's expand this further now. And let's do rect vrect test. And so I'm going to grab, once again, our rectangle. I'm going to keep this as a reference. All right, I'm going to rename this one R1. And I'm going to make another one. And we're going to have an R2. All right, now if we want to determine which one is colliding, we're going to want to do the same kind of a test. I want to be able to project as fast as I can and say that these are not colliding and only have to worry about when we're overlapping to then worry about it doing any additional work. So how do we do that? Well, it's going to look remarkably similar to what we did here. We move it on up. Give us some more room because we're going to have to expand this. So what I want to do is check, so it's R1, R1, R2, R2, R1, R1, R2, 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 R2. Okay. I want to check to see if my right side is less than this left side, and then I can reject. Because if my right side is less than your left side, it doesn't matter what the other dimensions hold, I can't possibly overlap. So my right side is plus R1 dot width is less than your left side. And then the same thing on this dimension. My top, or my bottom, R1.h is less than your top, then I can't possibly collide here. And now here we're asking R1.x, so this is my left side greater than your right side, or is my top greater than your bottom, in which case there can't possibly be an overlap. And now we've just expanded it just a little further. We just basically took our point test and just added a little bit of dimension to it. And the rect v rect question remains. Now, let's keep our momentum going, and let's start talking about, didn't want a new window, wanted a new slide. Let's talk about circles. Circle v-point. So I'm going to take these two. So we've already dealt with the point. In fact, I'm just going to grab the point from here and deal with px and y. And now we're going to define what the circle looks like. And we're going to say that this is going to have, called circle C. We're going to have an x and a y and an r. So what we're going to have actually here is can I grab it? It's hard to grab it if that's small. Just move it physically. And now I'm going to arrange and align, center, arrange, align, middle. Cool. So this is the x and y, and then we have radius r there. So this is the position, and this is the radius. That describes a circle. So you have a circle would have an x and a y and an r. Now we want to determine if the point, I needed to copy that, if the point is inside the circle. Well, doesn't matter where we are around it. Since circles are the same from all directions, all we need to do is determine the distance here. So if this distance is less than or equal to this distance, then we have a collision. So how do we determine this distance? Well, we should remember from high school geometry our good old friend, the Pythagorean theorem, which is the a squared, how do I do superscript? Format text, superscript, yes. I don't want superscript anymore, hold on. A squared plus b squared. Nope. Equals c squared. So in this case, this is the c, and then let's pull this out a little bit. There's a method to this madness. There we are. Cool. Wow, I'll end it up pretty well. So we should remember, let's call that A. B. And C. So the length of the hypotenuse squared is equal to the length of the other two legs squared. This only works for right triangles, of course, which is what we're dealing with. We're basically dealing with a triangle here. So we can reorganize this. Actually, we can even rewrite this. So B in this case happens to be the difference, the delta between the x positions of our two positions. So B is, we'll call this P dot x minus C dot x. And honestly, the direction that we're asking this question in doesn't matter because we're going to find a distance. And since we're squaring it, sign doesn't matter. So if it was positive or negative, it doesn't matter. It's going to be the same thing. A is now going to be, in this case, the y's. So P dot y minus C dot y. And C now equals, we can reorganize this equation so that we have the square root of A times A plus B times B. And we can substitute all of that out, and we end up having, what did I just do? Let's rewrite this whole thing as a single piece of code. Just substituting here. Paste. 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 And paste. Oh, and look, let a semicolon, and now it's code. And we would actually make this lowercase because that's actually the mathematical function that we would have in this. So we would have that to determine the distance between P dot x and C dot x. And then all we have to do for the question is to ask if C is less than or equal to C dot r, collide. Or we can say if it's greater than, reject. And there we have it. That's how we would do that. All right, that's circle versus point. Let's talk about circle versus circle. For this, well, we're not going to have P, we're going to have C1, which has an R. And we're going to have C2, that's going to have an R. Delete you entirely as well. Copy, paste. And now we need to determine, we've got two different circles of different radii. It's going to be the same kind of a thing here where we need to determine this line. So from this point to this point, this is what we need to now compare against. So it becomes the exact same thing. We need to compare the centers. Only in this case, instead of being in P, it's going to be C1 and C2. C1 and off. I'm just going to copy paste. 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 Honestly, I might be doing these backwards too. Just checking each dimension. Wait, no, it's the same thing twice. Only here, what we're not doing is greater than CR, we're doing C1R plus C2.R. So if the combined radii is less than the distance, then we have a rejection here. Or another way of saying is if the distance is less than our combined radii, then we are colliding, then we are touching. So that's circle versus circle, and point versus circle. It's the same thing. It's like the same thing when we advance from rectangle to point to rectangle to rectangle. It's you just add in the additional dimensions on both sides, and it still works the same. Okay, let's now talk about combining them. It gets a bit weird. One thing before I even do this. We don't, square roots in code are work, particularly when we're working with floating point square roots. It does, I believe, the way they do this is they actually just run Newton's approximation, which is if I remember correctly, about 2 divisions worth of work. And then they take the output of one and feed it back into the equation. And the more they run this approximation equation, the closer and closer we get to the actual level. And with floating point 16-bit floating point integers or 32-bit integers, I think it can do this with 11 iterations, and it guarantees that it's more accurate than we can store in precision with a 32-bit floating point number. It's a long way of saying that every square root we're doing with a 32-bit number is 11 floating point divisions, which is a lot more work than, say, floating point multiplication, which is certainly more work than adding or subtracting. So square roots are the enemy, particularly if we're doing something in loop. Like if we're doing, like, again, a bullet hell game where we've got like 8,000 things on the screen, each one of them doing a circle square root check, that can be a lot of math that finally adds up and impacts performance. So we can actually avoid this by squaring both sides. So what I'm going to do is get rid of the square root here. But then what I'll do is I'm going to square this side. Since all I care about is relative, then this gives me, for the price of, wait, these are supposed to be times. This is supposed to be times. For the price of one floating point multiplication, I've gotten rid of about 11 floating point divisions that I would have with the square root. And the same thing would apply to this as well. So this would be r times r, and then I can get rid of the square root. So one multiplication gives us the ability to avoid 11 divisions. I might be misremembering the actual numbers on that, so don't quote me on that one. Feel free to look it up. I'm not going to bother right now. So that's another thing to keep aware of. Square roots are sometimes unavoidable, but try to make sure we minimize them when we can do. In this case, it absolutely is avoidable. I'm only going to cover the next actually, let's talk about line intersections. Actually, I'm going to stop this video here. It's getting a little bit long, and then I'll put the more advanced collisions in the next one.